I'll just wait for people to come in now.
Yeah. Do you hear me?
Yeah, I've got you.
Okay.
I've got 12 people in now.
Okay. That's enough.
I'll give it 30 seconds before we start. Okay, I think we'll make a start on this webinar. Just for everybody, my name is Mike Langton. I'm one of the senior application engineers at Guideline Geo. I am going to hand you over to my colleague in just a second, Jana. She's going to take the main event here and the presentation. But just before Jana starts, just a quick introduction for people that haven't been on this webinar before, or this webinar platform. Just above my head there, there's a reconnect button. If you lose connection, or if we freeze, if we stop talking, and Jana and I never stop talking, but if we stop talking, just hit that button up there. That often just reconnects you. Down the right-hand side of the screen, you've got the chat box. That's the best way of communicating with us. You can ask questions at any point. I will be monitoring the questions throughout the session, and if there's any very quick questions that I can answer quickly, then I will do that. If there's anything that needs a longer description, then we will leave that to the question and answer session a little bit later. So everybody's saying hello, so everybody hi. And I think at that point then, oh, by the way, if you want to mark your comments as a question, you can do that, and also you can mark it as private, and just Jana and I will see those questions, nobody else, and we'll just refer to you as your first name or your initials if we're going to reply to you on that one. And I think that's all about from me. I will disappear for a short while. I will come back at the end. And with that in mind, I'll hand over to the wonderful Jana.
Hello, everyone. I will just share my screen, and then we can start. Okay. GPR. From rebars to glaciers. That's today's topic. Let's see. So, welcome everyone. My name is Jana Gustafsson, and I have been working with the geophysical investigation since more or less 1993. Actually, I started with resistivity measurement and long-term monitoring of contaminated groundwater. But after that, I have more or less been working with just GPR measurements. It's more fun. So I have been at Malmö Geoscience, I have worked as a consultant, and now I'm back at Guideline Geo since last year. Today's content of this webinar will be shortly the GPR method. What is GPR? What's the trace? What do we do with different antenna frequencies? And what's a GPR system components? And after that, we will look more into detail in different types of applications. We look at applications from the size of rebars to glacier and ice measurements, the large scale side of GPR measurements. So let's start. What is ground penetrating radar, GPR? It's a technique that employs high frequency pulsed radio waves with the frequency of 10 to 4,000 megahertz to acquire information from the subsurface. With GPR, you can see metallic and non-metallic structures, features, and layers buried in the ground or in man-made structures, meaning that you can take your GPR out on a field or measure on the house you are living in. It's not like an X-ray, but more like a fish finder that you can have on a boat. And all modern GPR systems consist more or less of these three system components. You have a data logger. It can be a dedicated monitor or a laptop or a smartphone or other devices that collects the data. You have the control unit. That's more or less the brain of the system. The control unit takes care of these electromagnetical pulses, so they are sent in a correct way and also received in a correct way. And then you, of course, have the antenna. That's the one that actually sends out the waves and receives them again. And in one antenna box, you always have a transmitter antenna and one receiver antenna. And then you also need to trigger the data collection in some way. So that is more or less always done by wheel with a pulse encoder, or you can also do it by time or by keyboard triggering. So that's the GPR system, more or less looking the same. And with GPR, you measure something called the trace. One trace is one measurement point, but the trace consists of several parts, so that actually gives you information from one position, but all the way from the ground surface and downwards. So you have your transmitter antenna to the left and your receiver antenna to the right. And when you start to send these electromagnetical pulses, the transmitter starts to work, and the pulse propagates through the media, through the ground, and also along the fastest way from the transmitter to the receiver, along the ground or in the antenna box itself. And when it hits the receiver, you have a amplitude on the trace telling you something about how strong the reflection is for this electromagnetical wave coming from the transmitter and hitting the receiver. So that's why you get this huge oscillation on top of the trace. But some part of the energy still moves downwards in the ground and hits the target. And when that rebounces to the receiver, you get a smaller oscillation on your trace, saying something about the amplitude of that reflection. And then when you have collected this trace a certain amount of time in nanoseconds, you have your full depth of your investigation. So this is a trace. It bounces from plus to negative around a 0 amplitude, and those bounces say something about the strength of the reflection. So we turn these amplitude values to a grayscale, and then we collect these grayscale stripes, for instance, with 5 centimeters apart along the ground, and by that create our radargram, which is the resulting picture of a GPR investigation. So GPR work is much about dragging, pulling, taking this antenna with the transmitter and receiver and just walk and walk and walk. Most often it's not as smooth as in this picture, going on ice and snow, but the terrain in especially Swedish forest can look like this. So if you want to train during work, GPR measurements are quite nice. So we had the radargram consisting of a number of different traces, and this is the result of the GPR investigation. So what can we see in a radargram in the resulting picture? We can see two types of reflections. We see planar reflectors and we see point reflectors. So layers in the ground or in a building will also create layers in the radargram, while points will be these up and down, these hyperbola-shaped objects in the radargram. We can also look at the structure in a radargram. For instance, if you are working in a forest, you will have a different type of structure if you are measuring in a till with boulders and stones compared to if you are measuring in homogeneous sand. So the structure of the radiogram is also important, especially when you work with the geological applications. So the hyperbola, why do we get this strange type of shape when we are looking at point objects? This is due to the fact that the GPR signal, these electromagnetic waves, do not just go straight down. They will spread. It's more like a cone. So when we move with the antenna along the ground, the pulse will spread, and we actually will sense objects before we are on top of them. And we will also sense the object when we have passed it. So this makes the hyperbola shape of objects in a radiogram. And when we talk about GPR, we often talk about different antenna frequencies. The antenna frequency gives us the resolution and the depth of the measurement. If we have high frequency antennas, we have a short wavelength, and by that we have high resolution. So we can actually see small objects. But the energy of that type of antenna is not that good, so we can't see that deep. But with low frequency antenna, we have a huge wavelength, meaning that we have more energy in that wavelength and we can see deeper, but we lose resolution. So in this example, you can see small hyperbolas on top, in the top radiogram. That's heating pipes in the street. And we can't see that deep, maybe 1 meter down. And in the bottom picture, we can't see any trace of those hyperbolas. So the heating pipes are completely disappeared, but we see structures at 2, 3, and 4 meters depth instead. So with GPR, you have to consider what resolution you want and what investigation depth you want. And as you also see, depending on the frequency, the antenna itself has different sizes. So high frequency antennas are small and low frequency antennas are bigger. This is due to the fact that the antenna element itself has to have a certain size to build the wavelength of that antenna frequency. To see small stuff in the ground, these need to be on top. You can't see minor objects on bigger depth. That has to be remembered. So looking at small coins, those need to be close to the ground surface, and you can't expect to find single minor details 10 meters in the ground. And most often, the limit of ground penetrating radar is approximately 50-60 meters in ordinary soils, and the target size is approximately at minimum 0.5 centimeter, and then we have the whole range in between. So low frequency antennas sees deep, but the target has to be big, and high frequency antennas don't see that deep, but instead see smaller details. We also talk about single and multi-channel antennas. To the left, we have a multi-channel antenna, and to the right, we have the single channel antenna. Even in the single channel antenna, we actually have 2 antennas. We have the receiver and we have the transmitter antenna. This is the most common GPR antenna. It's a box with 2 antennas, and you do 1 single 2D line. With a multi-channel antenna, you combine a number of transmitters and receivers and can measure several 2D lines at the same time. This gives you high density data which can be combined to 3D volumes and giving you very good detail of how the ground conditions look like. For instance, for archaeological purposes or complicated utility surveys. But when you are looking at geology and layering, the 2D radar is more or less the most efficient way to work. So depending on the application, you bring along your GPR antenna in the most convenient way. You can push it, you can pull it, you can have it behind the boat, you can have it behind vehicles, you can put it on a string, on a wall. Yeah, you can take your skis, your snowmobile, everything to make field work as easy as possible. So if GPR data looks like this when you are out in the field, then you are ready to go and can continue. But from time to time, you have GPR data looking like this. And then you have to actually stop and think, okay, is GPR the most suitable method for my application today? Because GPR doesn't work in every environment we have. These electromagnetical waves don't like conductive conditions. When we have ions in the ground, for instance, clay or contamination, they will just take all the energy out of your electromagnetical waves, and you don't get any information from the depth. Sometimes like 5 centimeters of clay can ruin your day completely, as well as seawater or a site where you have contaminations. And then you actually have to change your physical method and try to work with resistivity or something else instead, because ground penetrating radar and conductive conditions is not a good match. But if the picture looks like above, then it's just good to go and continue your work. So this was the short introduction to GPR, and now we will talk about different types of applications. And we start with the small ones, the rebars. This is a project in Sweden where the aim was to map load-bearing rebars in walls. It's a water power plant where the walls were so bad, so they actually have to drill and do concrete grouting in the walls, so they should stand up. And of course, when drilling in this type of construction, you don't want to hit those load-bearing rebars in the walls. So ground penetrating radar were used and to mark the rebars on the walls with paint when the measurement was done. So in the radargram, you can all see the big hyperbolas a bit down in the radargram. That's the load-bearing rebars, and above you have a net of let's see if we can paint something. Up here you have a number of small hyperbolas. So actually you have two nets or two types of rebars. You have the small rebars close to the wall, and then you have the big ones down here. And when marking these rebars, you actually know that, okay, I can drill in between here and do my concrete grouting. Like that. And you can, of course, also measure on floors. This is a quite clear example of a a rebar mat at different depth. You have the hyperbolas, and then you have a clear layer beneath those hyperbolas, and that's the actual thickness of the floor. And then suddenly all the hyperbolas disappear, but the thickness of the floor seems to be bigger. So one part of this floor has rebars, and then you can decrease the thickness of the concrete. But when you take away the rebars, you actually have to have more concrete to have the same stability of that floor. And you can also look at the layers within the construction. In this case, we have on top rebar, a net of rebars, and below heating pipes. This measurement is done with dense parallel lines, which are combined into this 3D volume, where you can actually go up and down in that volume to look at the different rebars and heating pipes within that measured volume. And again, this is nice to know if you have to drill or do any changes in that construction. And talking about constructions, GPR can be used for a number of different applications for constructions. Most often, new constructions, you have drawings, you know how the building is done or made. But if you have older houses, maybe the drawings are gone and there is no information on how the building was constructed. So GPR more or less always give you some information on the construction of a completely unknown building. In this case, we have a ice hockey rink, and to get that perfect ice all the hockey stars want, the concrete has to be very, very even, but not too even so that the rebars or the heating pipes in the concrete itself comes too close to the surface. So GPR is used to map the amount of concrete above the rebars, so you know where you can take away some concrete to make this ice hockey rink more even, to get that perfect ice. And the color scale on the right shows you the amount of concrete. So in the red spots, you can't take away any concrete because the rebars are too close. And in the blue spots, that's okay because there the rebars are deeper down. So also measured in dense parallel profiles and treated like a 3D volume when presenting the results. You can use GPR to map voids in walls. This is a high frequency antenna seen to the left, and then the resulting picture on the right. It's a part of a wall, a so-called sandwich wall. So the elements of the wall is ready, and when they install them in the house, they actually fill that sandwich wall with concrete on the building site. And then it's of course important to fill whole the area between these sandwich walls with concrete to avoid to get big holes. As in this case, the white spot in the upper left corner is actually just empty space between two sandwich elements of concrete. So in this case, the neighbors can most likely listen to each other's dinner conversations because we don't have done this wall correctly. You can also use GPR to map different hidden spaces, typical police work. But in this case, it's an Swedish castle where somebody thought that Marie Antoinette's gold treasure were hidden. So we use GPR on several different locations to find hidden spaces behind the walls. In the middle, you see one single 2D line measured horizontally on the wall. So on the left side, let's see if I can draw again. Here, you can see rebars, and then you see this even spot, and then again rebars. So this corresponds to rebars here, not seen in this picture, and then the empty spot or the even spot in the middle here, and then again wall. When we have put several of these 2D lines together and made a 3D surface. So it's a hidden empty space behind that wall. But unfortunately, when they open it up, it was also empty, no gold treasure. So I still have to work for my living. Let's continue and turn that off. Yes. Old building with no knowledge of how they were constructed. These are two medieval walls in Sweden where actually the acid rain has made the walls to deteriorate, and meaning that stones actually will loosen and fall down. So it's a risk to be close to these constructions. And these areas are quite huge, and it's hard to know how to test which stones are actually firmly still firm and which stones are coming out. But when doing ground penetrating radar work, you can get this type of pictures because when the reflection strength is big, as in the red parts, you know that, okay, in these parts, I go from stone to air to stone, meaning that the concrete between the stones actually has gone due to the acid rain. So in areas where you still have stone, concrete, stone, you don't get that clear or high amplitude in the reflection between the stones. So to the left, that part of the wall is quite okay. It's more or less homogeneous. But to the right, you have a stronger reflection, a stronger amplitude, meaning that these stones are more or less likely to have less concrete around them and are ready to fall down. And you can also look at larger areas to try to find underground constructions. In this case, it's a huge parking lot in the middle of Stockholm. They knew that, okay, we have old bomb shelters in this area, but we have forgotten where. And when you want to build or load this parking lot more than you used to, you need to know where you have these type of constructions so you actually know how to construct something above it. So again, a number of parallel profiles with an ordinary single channel GPR equipment. And when looking at 1.5 meter depth, we can see, let's see, we can see these square constructions, 2 of those. So the bomb shelters were easily found with GPR, and also the staircases from those shelters up on the parking lot. Mission completed. If we continue finding different stuff with GPR, utility is one of the most common common application you can work with GPR. The easiest, of course, is when you have a case like in the top picture. You have 4 utilities quite close to each other, but they are easily seen. So this type of work can be made really efficient because you can actually just mark the utilities directly on the ground while measuring, and then you are ready with the work. In Sweden, we have plenty of till, meaning that we have boulders and stones and sand and really heterogeneous ground conditions. And that also makes utility service quite hard. As you can see in the picture below, there are a number of hyperbolas, and when working in parallel profiles, as you can see to the left, it's hard to distinguish which different hyperbolas are connected to which, and which are actually utilities and which are actually just single boulders or stones or tree roots or whatever can be buried in the ground. So utility work can be quite easy and sometimes really tough, depending on the surrounding geological conditions. One type of utility is, of course, other stuff that is buried in the ground. In this case, oil drums. As you can see, it's a parking lot, an estate that were supposed to be sold. And they wanted to know if the old oil drums were taken away or not, because that's an environmental question. A number of parallel profiles, all the black ones made here. Yeah, in 2 directions. And all the red dots in this area corresponds to these nice hyperbolas. So you have 3 oil drums laying still in the ground. The blue ones and the pink ones form the pipeline to those oil drums, and all these green dots correspond to this type of hyperbola. You see that it's like a white-black stripe going direct from top to bottom of the radiogram. It is so-called ringing, so most likely all these green objects are metallic, because metallic objects create this type of ringing signature in the radiogram. So in this case, really clear hyperbolas for the oil drums. Sometimes data is not that nice, as in this case. The neighbors living here complained of a headache and said that there has to be something in the ground that makes us feel bad and have a headache. I did GPR measurements along this road and got this weak indication, both as a top view and as a 2D view, and said that, okay, I'm not sure because ground conditions are quite bad, but you should dig in this area. And they actually find the oil drum. So even though the ground conditions can be bad. You can because this was a huge object, and in metallic, it was seen in radar data. Yes, and talking about utilities and complicated cases, if you have large areas and utilities in many different directions and on many different depths, a better idea than to work with the 2D radar is to do multi-channel radar work to get these high resolution pictures of the ground situation. So to the left, there's a parking lot with a number of different utilities. And to the right, it's a bit hard to see, but that's a soccer field with a really nice fishbone-shaped drainage pipe system. Both are made with multi-channel radar to get this high resolution of the utilities. You can also use ground penetrating radar to search for old stuff, historical stuff, archaeological investigations. It's nice to try to find treasures. This is a medieval church in Sweden where they had suspicious that below this big stone on the floor, there could be something hidden. So we did dense parallel lines over that stone. You can see the same fracture on the stone itself and in the top view of the radar data. And when going deeper down below the stone itself and to the ground, there are two black spots revealed, and more or less in that position. So this is a strong indication that they should actually lift on that stone to see what's below it. They haven't done it yet, but I hope they will, so it can be revealed if it's two small stones or actually something more fun, like a treasure. You can measure in modern churches inside, because in Sweden it's quite common that if you have a medieval church, you build a modern church above it. So when you want to know where the actual location of the medieval church has been, it's quite nice to measure in the modern church and reveal the location. As you can see, quite common in Sweden is this round-shaped apsides of the church, and this is quite clearly seen in the radar data, measured on top of the wooden floor in the modern church. So that's a way to locate the medieval church within the modern church. Let's turn the whiteboard off. And this is the city wall of Birka, a Viking Age village in outside Stockholm. So here the multi-channel radar was used to actually map the city wall. It can be seen here, the parts of the city wall, and then we have a gap, and then the city wall continues. So this is actually the gate to the village. And here we can also see small dots like a band of pearls. And that's the remains of a wooden palisade, which were constructed to keep foreigners out from that village. Let's see. And when working with multi-channel data, you get really nice resolution. So this is just examples on good archaeological investigation using GPR. The left one is from England. It's a Roman fort. And the right one is a Viking ship found in Norway not that long ago. But GPR can be used to actually map features in nature as well, and not just man-made objects. So tree roots can be detected by ground-penetrating radar. We have this huge pine in Stockholm. I think it's like 300-400 years old. And as it's situated in central parts of Stockholm, it's really expensive and they want to preserve it in any way. Unfortunately, the estate where the pine is located was sold, but the city still wanted the pine to live. So they decided to map the root system of the pine and actually move it to the other side of the street. So to be able to move it, they wanted to have some information on the root system. So we did the single channel ground penetrating radar measurement. It's all the black lines in the picture to the right. And then the different marks are for blue and red, that's utility lines. And then the pink ones are actually the root system. So the ground penetrating radar investigation revealed that on the left side of the pine, the bedrock is steeping quite fast. So the roots are going more or less directly downwards. And on the right side of the pine, the roots are laying on top of a even bedrock surface. So that gave them a good idea of how to attack that pine and actually move it like 50 meters and replant it. So this was 2D radar, and when looking at tree roots with multi-channel radar, it can look like this. Of course, much more details. And really nice to see the structure of the roots. And you can also use ground penetrating radar to look at the sinkholes. That's a huge problem in certain type of environments, geological environments, and can cause really bad damage. So this radargram is made on top of a limestone, and a sinkhole and then when looking at the area invested, Okay, I hope I'm back. I lost my Wi-Fi connection.
Yeah, you're back, Jana. It's okay.
Okay, let's start again with sinkholes with multi-channel data. This is measured on an huge asphalt area, and we have these two anomalous parts, both black. And when looking at those in 2D, we can see that there's a big difference in compared to the surrounding. So these indicate that we have sinkholes in the area. And then we also have this small structure here. It's not completely black. It has black borders, but then it's more or less homogeneous in the middle. So that's actually a sinkhole which is refilled. Okay, now we can talk a bit about railroads. That's also quite common for GPR investigations. Sometimes you have to work by pulling your GPR along the railroad in snowy conditions. It's hard work, but fun, and it's nice when you get that nice result. In the radiogram below, the red line represents the actual ballast of that railroad. And as you can see, it has deeper parts where we have really high embankments of the railroad. The green features are bedrock seen below that railway. And looking at the data in detail, you can actually see parts where you have plenty of hyperbolas. In this case, it's fascine work with old tree trunks used to improve the carrying capacity of that embankment, railway embankment. And when you don't want to walk anymore, you can actually use a trolley and connect your GPR to that one and take a bike ride along the railroad. In this case, they wanted to know the geology below the ballast, the embankment, because they were to change all the poles for the electrical wires, and they wanted to know if those were to be founded on bedrock or in soil. So the main purpose was to actually look at the geology below the ballast. But as an extra result, they also got the amount of ballast to check the quality of the railroad. And when you don't want to go by bike, you can actually put the GPR on in front of an actual train. So you can sit inside instead and just move along in a nice way. And from railroads, it's not far to roads. That's also quite typical for GPR measurements. Then you actually have the antenna. You can have the antennas behind the car and just drive more or less in the same speed as the surrounding cars. Road mapping most often has the purpose to look at the asphalt layer and the internal layers of the road embankment to see the need of reconstruction. So when doing road measurements, most often you combine two different antenna frequencies. You want a high frequency antenna to look at the asphalt layers, and then you want a antenna with a bit lower frequency to look at the internal layers of the road itself. To the right, it's just an example of how you can present your result, where the color scale says something about the thickness of the interpreted layer. And if you want to go deeper, you just combine your high frequency antenna with the lower frequency antenna. So in this case, you have a really high frequency antenna for the asphalt, and then a low frequency antenna to look at also peat and bedrock underneath the road itself. And as you can see in this picture, we have also geotechnical information. So that's more or less always needed when working with geological investigations. You want to have some points of geotechnical information to make your interpretation of the ground penetrating radar as good as possible. And you can also use ground penetrating radar to look at the difference between a concrete road and a normal road. The red part of the radiogram represents the concrete road. I can't actually see the concrete itself, but what I see is a large number of small hyperbolas. So that's actually the rebars within that concrete road I can detect instead of the concrete itself. So this was a project where they wanted to dig along this road to construct a new main water pipe, but they didn't want to dig in the parts with the concrete road because that would have cost too much money. So in those parts, they actually lay the water pipe along the road instead. So again, it was easy to just put the ground penetrating radar after the car and drive for 20 kilometers and mark the areas with concrete road. And this is just a detailed picture of asphalt. As you can see in the middle, it is quite thick. In this part, there's something wrong with the road construction because they have put on more and more asphalt as the road is sinking. And you can also see that the asphalt is layered because they have done it several times, but it also has quite homogeneous structure compared to the layer below the asphalt. Here, in this part, this is actually the reinforcement layer with the more coarse grain material, which appears as a structure of thousands of small hyperbolas. So this is one way of looking at the structure in the radiogram, where it's more homogeneous or where you have all these small hyperbolas actually representing more stony ground. And when talking about stony ground, we can continue with geological investigations. Bedrock mapping is the most common thing you use ground penetrating radar for, at least in Sweden. Most often you need to know where you have your bedrock if you want to construct a road, a railroad, houses, whatever. And if it's a long road, you can't do geotechnical drilling along the whole or as dense as you actually need to get a good grip of the bedrock. So the best way to work is actually do ground penetrating radar first, do a quick interpretation, and then decide in which points you actually want to drill. A traditional geotechnical investigation would have done the drilling at even distances and then just drawn straight lines between those points, and that would be the bedrock. But as you all know, the bedrock is undulating much more than that, and it's seldom very even. So it's good to combine ground penetrating radar measurements with drillings. And when you get the results of the drilling, you redo your interpretation, and that actually gives you the most correct information on subsurface conditions. This is a nice esker in Sweden. So it's only soil layers. Sandy material, fine grade sandy material often creates these nice layers. More coarse grained sand looks very homogeneous. This is the parts which is more evenly gray. And then at the bottom, you have the till with more stones and boulders, creating this structure of plenty of hyperbolas. This is also a geological investigation with an 80 megahertz antenna to go as deep as possible, because the objective of this work was to find areas where they could try to withdraw groundwater. So ground penetrating radar were done over a very huge area. But as you can see in the top right picture, the red represent shallow bedrock and blue deep bedrock. So the area wasn't that good for groundwater at all, because the bedrock was more shallow than they thought from the beginning. But this work took 1 day in the field, so it's quick to get an overview over the geological conditions with the ground penetrating radar. So to take a decision on to continue or try to find another spot for what you want to do. This was a work to look at the conditions for groundwater infiltrations. They wanted to avoid areas with clay, so ground penetrating radar was used to look at this sandy material and try to map clay lenses within that sandy material. As an extra result, we actually saw the groundwater level. It's seen as the horizontal lines in both of these radiograms. I wouldn't recommend to use ground penetrating radar to actually look to map groundwater levels, because it's so depending on the grain size of your soil material. If you have fine-grained soils, the capillary fringe of the groundwater is quite high, so you don't get that clear contrast between dry and wet material. The groundwater level will be really diffuse or not seen at all in ground penetrating radar data. But in areas where you actually have coarse grained sands, you can from time to time be able to see the groundwater level. But for me, that's just good extra info and not the main purpose of the work. You can also measure directly on bedrock to look at fractures. So this is just an example of a radiogram with the interpretation of fractures within the bedrock. And if I hadn't done the investigation, for me, the top radiogram looks as an ordinary radiogram measured on soil. So it could also be interpreted as soil layers. So bedrock is funny because all the fractures actually can look like soil layers and not bedrock. And then, of course, you can also map limestone. This is a quarry in Sweden where they wanted to know how much, which is the volume of limestone you can take out and use. So ground penetrating radar, GPS, a long snakely-like profile, interpretation, and then you get the volume of the limestone. Peat is more or less the simplest thing you can actually do with ground penetrating radar. It's such a nice contrast between the peat and the surrounding soil material. As you can see, there are 3 points of drilling, handmade drilling, so they have not reached the bottom of the peat. So in this case, the ground penetrating radar was much more efficient to actually look at the thickness of the peat. And if you have large areas, put the GPR behind a four-wheeler or a snowmobile and just go. You can see the track in the middle and then the interpretation of the thickness of the peat on the right-hand side. You can also, of course, put the ground penetrating radar in boreholes to look at the bedrock. You can do it in single holes, or you can do it in 2 holes where you have the receiver and the transmitter in separate boreholes to look at the condition of the bedrock between those boreholes. And we can measure on lakes and rivers. What you have to remember with the lakes and rivers is that the conductivity of the water is really important. Ground penetrating radar won't work in seawater because it's too salt, but it won't either work in environments where you have a light, where you have plenty of nitrogen or phosphorus, because that also creates a conductive environment for the ground penetrating radar. You can have the radar antenna in a boat. Make sure it's a wooden boat or a plastic boat. And the easiest is if the boat has one single bottom and not double bottom. Because if you have water in that double bottom of the boat, you can get a nasty ringing of the ground penetrating radar signal and actually don't see anything. And on the right hand side on top, you see the water, you see till and bedrock, and on the radiogram on the bottom right, it's again water, the bottom of the lake with nice hyperbolas. So that's some objects laying on this lake bottom. Nice application is to look at sedimentation at water power plants. The sedimentation makes the volume of the dam to decrease, so you can actually gain less electricity. So it's the water power plant wants to know the amount of sedimentation so they can actually clean the dam from time to time to get the dam to be as big as possible. And if you want to go really deep, you can use low frequency antennas and actually put them in an ordinary plastic sewage pipe and drag them behind the boat. And you can also do river investigations along a river to look at the river bottom. From time to time, rivers can be quite harsh. They can be too flooded, have high pace of the water. and can be quite dangerous to be on. So then you can put the ground penetrating radar on a drone and actually do the measurements from air instead, so you don't have to be on the running water. And then finally, we have the last application area of ice, snow, and glaciers. Snow, ground penetrating radar is quite good for snow. You actually also can see the internal layers in the snow, and snow is clean and nice, so high frequency antenna sees quite far. Mapping ice, perfect if you have a test site for new cars, plenty of those up in North Sweden, and before you let your expensive cars out on the ice, you actually need to know the thickness of the ice. Of course, otherwise those cars will take a swim. A bit more of ice is the Greenlandic ice cap. In this case, we see ice down to 40 meters, plenty of fractures, but nice working environment. And then finally, the glacier in Himalaya, where we actually have, with the 20 megahertz antenna, a penetration of several hundred of meters, and the possibility to look at both cold and temperate ice and also see the bedrock. So just to finish, some limitation and advantages. As I said, the penetration depth and ability to locate targets with GPR is really dependent on the conductivity of the ground. If it's too conductive, ground penetrating radar won't work. So that must be remembered. And you also need a contrast between the target and the surrounding material to make these electromagnetic waves to bounce back to the receiver antenna. I think that anyone can learn to use a modern ground penetrating radar system in some hours, but the interpretation of the data is more complicated. So you need a conceptual model of the ground, of the building, of the railroad to make the interpretation as good as possible. And you also need points of drilling, of sampling, to make that final step of good interpretation. But for the advantages, it's a non-destructive method, of course, easily handled, fast data collection, which makes it cost efficient. It gives you high detail of the ground and buildings. It finds metallic and non-metallic objects, and it's perfect to give you information between traditional point-wise investigation. And I think that the biggest advantages is actually that it's so fun, and only your imagination sets the limit of what you actually can do with ground penetrating radar. So that was all for me. If you have questions, you can always contact me by email.
Jana, that was absolutely amazing range of different applications there. So I think a virtual round of applause on that one. Could you just go back to the 2D radiogram of the sinkhole, if you could, because that's the point that we lost you. There's been quite a few people asking if you could go back to that one. It was the first one of the sinkhole slides that you had, and just run through that one again,
okay,
if you could.
Yes. This one?
The one before that?
Okay. Here.
Yep, that's the one. Yeah.
Okay. Yes. This is a sinkhole in limestone environment. We have the limestone down here, and then we have the soil layers creating these typical pits going down and down and down. So this layering indicates that the ground is collapsing. Okay?
I think that's perfect, that. Yep. So I think we'll just see if anyone has any. Oh, and Raman has just asked if you can repeat the road utility mapping as well.
Which one was that? Road utility.
Yeah, I'm not sure. Raman, was that the actual road measurements or the physical utilities themselves?
Let's see where I can find my roads. We don't have any utilities and roads. This was the one with the concrete road. Did you get any information on which slide?
It hasn't come back to me yet.
Okay.
Oh, the utility. Is it municipality? Oh, concrete road. Okay, it's saying concrete road. I think it's this one.
Okay. Yes, in this picture, the road has parts with concrete and parts without concrete. And when you do a new main water pipe, you don't want to dig or destroy the parts with the concrete road. So it was important to know the location of the concrete before that project started. And I can't see the concrete itself in the radiogram, but I can see the rebars in the concrete.
We've had a few questions come through. Hani says, can we combine high and low frequency? I did say yes.
Yes.
But that is possible, 2 separate channels
Yeah.
at the same time. So if that's possible. And Florina is asking, can you please repeat about the limits of GPR in water-covered zones, I guess?
In water-covered zones, okay. If you have fresh water, then GPR will work fine. But if you have water with contaminants or salt, where you have a conductivity that is too high, that will also take away all the energy from the GPR wave, so you can't see anything. And that can actually happen even if you have a fresh water lake, but you have too much of nutrients in that water due to, for instance, farming land or loads of horses around that lake. So that will also destroy that fresh water and make it too conductive. So when you have too much ions, like phosphorus in the water, that ruins the GPR conditions.
Perfect. And Tanboon Ann is asking, from the radiogram, how do you interpret electric cable, PVC pipe, and metal pipe?
Metal pipe, if it's big enough, you can see the typical ringing. It's like a black and white band below the pipe. But otherwise, it's quite hard to distinguish between different materials from a radiogram. You can't say that, okay, this is wooden stuff and this is plastic. The only thing that you actually can distinguish is when it's metal and you get the typical ringing.
And that can be quite difficult when you have a cable and a pipe roughly about the same size and the side, but it's very difficult to actually determine between the two. All we can see is that it's actually metal when it does have that effect of the ringing. So that's probably one of the hardest things to do, is actually physically estimate or calculate exactly what the feature is when you're trying to do utilities. That's one of the more difficult things. You need other technologies and techniques to ascertain exactly what's happening.
Yeah. And that's most often the case with the geophysical investigation techniques. It's good to combine them with other types of investigations as well.
Mm. There's a question here. What frequency antenna? It says has used small clay pots and clay objects. So I'm guessing looking for ceramic, maybe archaeology and that type of thing. I'm guessing with Chandana.
Yeah, I think that the most common frequency for archaeological purposes is around 500 megahertz.
I think that is definitely the go-to frequency for that type of application. Absolutely, it gives you good resolution, and it's reasonable resolution, reasonable penetration. So it's that good combination there, and also to detect animals and human bones. The bones itself are actually quite difficult. You can find the burials, you can find structure of the burials. Physical bones is actually quite difficult. They're not very reflective themselves, but the whole burial itself can be in that case. So that can be quite difficult. And
looking at more modern graves, it's hard to see what's in the grave, but what you actually see is the edges of the digging.
Absolutely, the evidence of the actual change. Mats is asking, when out in a forest, when your sender, presume the transmitter, jumps up and down, what will happen to the results? That will have effect on the results.
Yeah, you get crappy data, but not crappy enough to prevent you from actually do interpretation on that data. So if you're working on a forest cut and they have left the forest on that cut, then you have to go on top of all that debris. Of course, it will affect the depth penetration and also the data quality. But most often, you will be able to see the bedrock. But of course, if you're looking for small details, if you want to do archaeological investigation and you have all these debris on top of the ground, then it will be hard because the antenna doesn't go in straight lines and it's on top of stuff. But large-scale bedrock mapping, it's more or less okay, even though it's terrible terrain.
These questions are flooding in. This is great to have all these questions. It's really good. So we'll stay until they're all answered. We don't mind. Can we use the frequency that has a wavelength greater than rebar grid distance to investigate the voids under rebar reinforcement? So voids under rebar, under concrete slabs.
Yes, you can see voids under rebars. I think it's hard to tell which antenna frequency you should use because it depends on the distance between the transmitter and receiver and the frequency of the antennas, and of course the distance between the actual rebars. So most often it's good to try several antenna frequencies to see which gives the best result in that type of environment.
And we have the classic question. I think this is the golden question really for GPR. Can we estimate a diameter size of a pipeline? That's one of the more frequent ones that we get. I
wouldn't do it, but I know that people say they can do it because there are so many stuff that actually affects the size of the hyperbola you see in a radiogram. For the first one is that you don't know if you cross the utility in 90 degrees. If you cross it in 45 degrees, the hyperbola will be bigger. And also the soil velocity affects the size of the hyperbola. So I would say that you can say that, okay, this object is bigger than this, but I wouldn't put any size.
There is the possibility as well where you have a non-metallic pipe
Yeah.
that you could get reflection from the top and the bottom.
Yeah.
We
Okay.
get the two,
Yeah.
but the key thing on that one is you need to know what's inside the pipe, because that will change the velocity and that will change the calculation for the two. It's not a precise value. It's definitely not precise. It's definitely approximation. And I think it's quite difficult, I would say, wouldn't you? To actually give an absolute, you know, it would very much be an estimate.
Yes.
And the next question is, could you describe how to detect military weapons buried in the ground? And that is just an object to us. It really depends on the size of the object and the depth and the material of that object to how we actually tackle that.
I would say that you need, if you work with single channel ordinary 2D radar, the distance between the profiles should be the same size or half the size of the object you are looking for. And if the area is big, I would go for multi-channel radar.
Absolutely. I think if anybody's these questions that are coming in, if you want to discuss this in a greater depth, then you can always drop us an email at any point. And there's various different ways of getting hold of us. And if you haven't got the web email address, then there's always our website. There's an inquiry form on the website. You can drop us any comments or questions there. I think I've covered all the questions and comments throughout this session. There was plenty. That was really good. Lots of interest.
That's perfect. Let's see. Now
Yeah, your last slide's got the email address on. I think so.
I will try to get it again.
I can put it very quickly in the text box as well. Oh, you've got it before I typed it in. Very good.
Okay.
Beat me to it.
So that's my email and the address to our website. And please contact us if you have any questions.
Perfect. Well, I think there's nothing coming in the last sort of 10, 20 seconds there. So I think at that point, I would like to say thank you to Jana on behalf of the rest of us, to say that was a fantastic and, like I said, very wide-ranging subject and topic. It was very interesting, some really good data in there. So thank you very much. Thank you to all the people that have attended. It's very nice to see everybody here. And we will have some more webinars maybe just after the summer period. So watch out for the comments and posts on social media, etc. And I think everybody's popping in now saying thank you. So that's great to see everybody saying thanks. We appreciate you attending, like I said. Any last words, Jana, before we go?
No, it was really nice. And I hope that you realize how much fun radar work is.
Absolutely. Well, thank you very much, everybody.
Thank you.
Stay safe.
Should I end the call?
Yeah, please. Yeah, just end the
event.
hit the button.